Hi, we're Project Scorpio, part of the Off-Road Student Association at Wrocław University of Science and Technology that has been operating since 2011. We come from various universities and consist of 5 different departments: mechanics, electronics, software, marketing, and science, all in all having over 40 members. We are one of the oldest and most titled teams in Poland, and we use our knowledge to promote the space sector in our country. Our team has traveled worldwide, taking part in multiple competitions and conferences. This year, we've already competed in Australian Rover Challenge in Adelaide. To organize and store our project, we use software such as Discord for communication, KiCad for electronics design, SolidWorks for mechanical design, GitHub for software cooperation, and ClickUp for task distribution. Physical work takes place at our small workshop in one of the dormitories. Here, we assemble and program the rover. We have access to basic tools and materials. External contractors make more sophisticated components. We test our rover in an indoor and outdoor environment. Basic tests are performed at the workshop, but more complex ones, like range and autonomy tests, occur at a nearby parking lot or an abandoned airfield. To expedite our workflow, the board makes most of executive decisions. However, the most important ones are being voted on by all the members. Our board consists of leaders from all 5 departments, as well as both association leaders and project manager. Department leaders are responsible for their own departments, being backed up by vice leaders, while association leaders work together to supervise and coordinate all departments and liaise with the university. Scorpio Infinity employs a dependent 4-wheel rocker suspension mechanism where rockers are linked by 2 triangular levers connected by a beam. This setup enhances overall stiffness and stability, enabling traversal of extreme terrains, including obstacles up to approximately 30 centimeters in diameter. Its exceptionally low center of mass allows to conquer steep angles up to 45 degrees. The rover's drive system comprises all-wheel drive powered by BLDC motors, which help the rover climb slopes in difficult terrain. Control signals for the mobility system motors are transmitted via the CAN bus, and individual motor control is possible through the operator app. To ensure optimal traction on Martian surface, specialized 3D printed tires are used. The rover fits within a cubic space, with each side measuring 1.2 meters. The entire suspension system weighs 36 kilograms. Our rover is powered by a 4S lithium polymer battery pack with a total capacity of 18,000 mAh connected to other modules via a 24-volt bus. The drive module is equipped with a visible emergency stop button that cuts power to the battery in an emergency. Every PCB made by us has protection against overvoltage, overcurrent, and reverse polarity. We use an NVIDIA Jetson AGX Orin as the main computer. We chose Jetson AGX Orin because of its ability to handle multiple video streams simultaneously and low power consumption. To connect each computer, camera, and other high-traffic modules, we use Ethernet connection. Other modules, such as the robotic arm, driving module, and scientific modules, use the CAN bus to provide robust communication. The rover's robotic arm has 6 degrees of freedom and weighs about 10 kilograms. Its design integrates planetary, worm, and harmonic gear reducers to optimize precision and stiffness. With a maximum reach of 1.2 meters, it can hoist objects weighing up to 5 kilograms at full extension. The gripper, actuated by a lead screw, ensures satisfactory grip strength. Moreover, the end-effectors tips are interchangeable, facilitating adaptation for various tasks such as soil sampling, and the effectors can be quickly replaced by a digger bucket. Made from carbon fiber, aluminum, and PETG, the arm strikes a balance between strength and weight. BLDC motors power the shoulder and elbow joints, while standard DC motors drive the remaining joints. Absolute encoders and custom controllers enable precise movement and position tracking for each joint, facilitating the incorporation of 3D inverse kinematics. This functionality is controlled by the Robot Operating System's Move It package, complemented by our custom-designed driver and planner. Certain arm positions can be stored as presets for easy navigation and streamlining operations during missions. For enhanced manipulation accuracy, a depth camera is installed to measure distances from the panel and display this information via our web application. This feature aids operators in executing precise maneuvers. To complete the first mission, our rover will be equipped with a scientific payload. The specifically designed drill mounted on the rover will extract samples that will later be analyzed in the science module named the Universal Terrain Exploration Platform. This module is capable of handling up to 5 samples, which will be stored in sealed containers to limit contact with the environment and potential contamination. Our primary tools for analyzing the samples will be a microscope, which will help investigate the microfossil content and mineral composition, and a Raman spectrometer, which will provide spectral data crucial for compositional examination. The spectrometer will also help in detecting organic compounds such as amino acids. All data obtained by the rover will be interpreted by our team at the scientific lab, where additional chemical analysis will be performed on the samples to evaluate the hypothesis. To maintain a strong signal with the rover, we created a rotor with a high-energy gain directional antenna. It is capable of autonomously tracking the rover in real time to provide the best signal possible. We're also focused on real-time bandwidth monitoring and data transfer optimization to create a much more stable communication system. The designed system will ensure a strong and stable connection at the Mars and Moon fields. The communication mast is modular and weighs 10 kilograms. Its height can range from 1 up to 3 meters. When extended over 2 meters, it is supported by a set of guy wires for stability. Recently, we put a lot of effort into autonomous navigation. We're able to avoid obstacles and navigate to GPS coordinates as well as to a point on our map. All Autonomy modules are fully written by us, ensuring perfect integration with our onboard hardware and other software modules. We're also able to detect and drive to different landmarks such as AR tags. To control the rover, operators use our custom-made web application. It enables us to control every module of our rover, monitor system status, display camera image, and other data gathered by the rover. The rover's base modules, such as the drive unit and robotic arm, are designed to meet the requirements of all the rover challenges we participate in. To adapt to a particular challenge, we work on the end effectors of the manipulator to prepare for all tasks. Thanks to precise fingers, a camera mounted on the gripper, and inverse kinematics, we're able to perform a quick and reliable switchover.